This is the last of the two video series on virtual memory. In this lecture, we will discuss the process of address translation that translates virtual memory into physical memory. We will also discuss how the operating system handles a page fault. This is the content that we will be discussing in this session. We will carefully understand the process of address translation from virtual address to the physical address in the main memory. We also talk about memory management functionalities such as memory sharing and protection. And finally, we will understand the concept of a page fault in light of virtual memory, what the operating system actually does to load or create the faulting page. So this was from the last time we said that the CPU generates a virtual address that serves as an input to this huge mapping function that is the MMU, the memory management unit, which will find the corresponding physical address in main memory, and the CPU gets to access the main memory. So this is what is known as address translation from virtual to physical addresses. But how do we perform that? How do we implement this mapping function? Well, this is the topic of this video, right? Let us get introduced to a new terminology, that is the construct known as the page tables. This is the way we are going to implement the mapping function. So a page table is going to consist of a set of array the page table entries that do this mapping for us, okay? Which is a translation from virtual to physical address. What we are going to use is our virtual address or part of the virtual address to index into this table. Find the right place, find the right page table entry, which will then contain the physical page number for where to go in the main memory, or tell us where on the disk we can find that page, so we can go and get it and bring it into the main memory and find the place for it, right? Now, this is a table that is in another part of memory, a part of memory that is kept in our physical memory, so that we don't have to go around and find that on disk as well. This table is stored in physical memory and is managed by the hardware, that is the MMU and the operating system. In short, the page table is the place in memory where we go and look up in that directory. That is the mapping between virtual and physical address. So 4 of these page table entries have actual addresses, physical addresses, yeah, that go to the physical memory. Then there are another 2 pages that we are using but are not resident in the physical memory, that are simply on the disk and would be swapped on demand if referenced by a process. Then there are another 2 page entries that are not allocated yet, that are not used for anything. However, they fill a part of our page table. So there again, those 2 gray colored pages have addresses to disk rather than to physical memory. And we know from the series on file systems that those addresses on disk have a very different structure. They are not 64-bit addresses. Rather, they have a different mechanism to index position on the disk. And that is done in a very different way. So how many page tables are there in our computer system? So let's think about that. We are going to need a page table for every process. And we know that every process are going to require a virtual memory. So there will be 1 page table for every single process. Now let's have a closer look into what address translation actually is. So this is our virtual address that is composed of 2 parts, the virtual page number and the virtual page offset. And in the first step of mapping process, we are going to use a part of that address, the virtual page number, to index into our page table. The virtual page offset has a similar use as in regular caches, where we have a block offset that is located by the block offset. Here, the virtual page offset is the offset within a page. We call that a virtual page offset. So we don't need those bits for now. We only need the virtual page number, the higher order to index into the page table. And then we read the valid bit, which will tell us whether this page is already in the physical memory or not, whether it is allocated or not. And if the page is not in the physical memory, this will give us a page fault, similar to a cache miss, in which case it will tell us that you need to get that page into the memory and try again. But if that is in the memory, then we will have a virtual page number, which then becomes part of the physical address, that is appended to physical page offset. The basic question that comes to mind then would be, where do we find this page table to look up for that virtual page number? Well, we will need a page table base register. This is a special register that the CPU is going to maintain for the process that is going to be done by the runtime system or the operating system to maintain where this table is resident in the memory. And for each computer system and operating system combination, there is usually a standard place in memory where that occurs. A very important note is that these things in most cases are similar to cache memories in that they are implemented in hardware and there is no software assistance or any knowledge of the programmer. Just for the sake of completeness, we look at this address translation from a perspective of a lower abstraction. How are they actually controlled in the processor level? To build a brief background into the control registers that are used by the x86 architecture to control the basic operations of our processor, these are some of the most powerful aspects of our CPU upon which the operating system is standing high. So we have these 8 control registers in the x86 architecture that changes or controls the general behavior of the processor. For example, interrupts, switching the addressing mode, our favorite context switch control, the paging control, etc., are all done using the CR. The control register CR0 has various control flags that modifies the basic operation of the processor. Important for our discussion here are the bit 0 that switches between protected and real modes. Then we have the paging bit 31 that enables paging. CR2 contains a value called page fault linear address. That is the attempted access to a page before a page fault occurred and is stored in CR2. CR3 is used for virtual addresses if the paging bit of CR0 is enabled, as mentioned before. We will see a diagram at a glance in the next slide. CR4 is used in protected mode to control some secure protected mode operations. CR1, 5, 6, and 7 are reserved. The CPU will throw an undefined behavior exception. The control register of prime importance in our discussion here, namely virtual memories, is the CR3 register that we said is used for this virtual to physical translation. So just a glance into the block diagram gives us what we need to complete the bigger picture here. So this is the CR3 control register, a 32-bit register that represents the 3 most important parts of the translation process that we talked about earlier. The first part is the page directory entry that are upper 10 bits from 22 to 31. The second part is the page table entry, the next upper 10 bits from 12 to 21. The third part is the actual address that we want to access for a particular task. Okay, so long story short, when the CPU is asked to access a virtual address, it uses the 10 highest order bits for indexing into the page directory table. The next 10 highest order bits are used to index into the page table pointed to by the page directory entry. The lowest 12 order bits are finally used to index a byte in the page pointed to by the page table entry. And we have a 4K memory page, right? So this is a 3-level structure that is used by some systems. In others, there might be more or fewer page tables required. So coming back to our discussion, this is from where we dived into the lower level abstraction. So in our case, we don't have the page directory as this is a 2-level structure. And we on purpose have made it simple for a good understanding of virtual memories. The operating system will typically maintain separate page directories and tables for each process, providing different mappings from virtual to physical addresses. This was our base address or base register of the current page table. which is a special register whose value is changed by the operating system during a context switch to another process. Therefore, although the indexes are equal for the process A, and process B, they index into different page directories. So now we have linked everything together, and we can move on to understand what do we mean by a page hit or a page miss. Let's see what happens on a page hit. So let's say this is the virtual address generated by the CPU, and we use this virtual address to index into our page table that is residing in the RAM. We find out that the address is valid, as the valid bit is 1, meaning that the page required by a certain process is mapped in the main memory. Okay, essentially that provides us with an address in the physical memory, and we now know where that page is, and we can access it using this physical address. So it's a two-step process. Look up in the page table to get this page table entry, and then we need a second access into the memory to get that data that we want at the physical address. What happens on a page fault? Well, a page fault occurs when we want to access a page that is not valid, and therefore its address is potentially going to be on disk or an uncached memory on disk. Why uncached? Well, because as we said before, though the page is allocated to a process, however, it hasn't been moved into the physical memory yet. So what we need to do in this case, for the obvious reason, we have to take that page and move it to somewhere in the physical memory. But where should that be moved in the physical memory, as it is occupied with other pages? Well, we are going to decide which page we are going to move out of the main memory. And because a process might require certain data from the moved out page in future, and that might create a page fault as well. So this replacement algorithm or the replacement policy must be smart enough to minimize page faults. Let's see what happens when a page fault occurs. So this is from the videos on process management, and we said that as the instruction of a process are being executed and it hits an instruction that references a page that is not present in the main memory, right? An exception is generated, and the control goes to the operating system that creates and loads the page using its exception handler. The exception handler is nothing but a table that is indexed by the exception number. So we know all this, right? So the page handler, after making the page available, it returns to the faulting instruction, and the move-L commands and the move-L instruction is executed again and is successful on its second try. Now coming back to our virtual memory. So what happens is that the virtual address goes to the page table. The virtual address goes to the page table to the corresponding page entry, page table entry, and finds out that the page is invalid and is resident on the disk drive. This causes a page fault instruction, right? Now the control goes to the operating system to figure out where to go and fetch that page from the disk and load it into the main memory and find a place to put it. So far, so good, right? So the first thing that the operating system has to do is select a victim page to evict. In this case, it happens to be the virtual page number 4. It is going to be removed from the physical memory. And how does the operating system remove it? Well, the operating system doesn't really remove it. It just simply changes the page entry to no longer point to the virtual space VP4. It rather changes that to VP3. Okay. Note that our page table is keeping track of the removed page that is now residing on the disk drive, and the valid bit has changed to a 0 to indicate that the page is no more in the main memory. The control returns back to the user process through context switch, and the offending instruction is restarted, and in the next run, it most probably gets a page hit. Okay. Now, let's look at the process of linking and loading in light of virtual memory. The idea of a virtual memory basically simplifies the process of linking and loading. As we know that the linking utility is responsible to link the symbol names in our object code. An almost complete image of our executable, however, needs to be linked to precompiled libraries or functions, for example, printf, scanf, malloc, etc. So these precompiled libraries are placed in pages that are shared by different processes, as highlighted before, that while implementing virtual memory, we want to be able to share pages to efficiently implement processes. Okay, so each program has a similar virtual address space that includes code, stake, and shared libraries that has a predefined location in memory. The loader, on the other hand, is a utility that loads our programs from the disk into the main memory using the system called execv. So execv allocates virtual pages for text and data sections, and that creates PTEs, page table entries, marked as invalid. The text and data sections are copied page by page on demand by the virtual memory system. Now, let us discuss how does a virtual memory manage multiple processes. Well, we know that the key abstraction is that each process has its own virtual address space. That is a simple linear array of bytes. However, now with virtual memory, this simple linear virtual space need not be contiguous in physical memory, because now we are mapping things at the level of pages or blocks of virtual memory. We can put any virtual page at any location, at any physical page in physical memory. So we don't have to worry about the order of these virtual to physical mapping. Okay, this is our virtual address space for two processes, and this is our physical address space in the main memory. Virtual addresses are mapped to the physical address in random order. So these can be scattered throughout the physical memory and can be in any order. So this helps us really fit things in as needed on demand and not have to worry about moving things around, so that they are always in the exact same order. And how does a virtual memory help with protection and sharing? Well, in the case of sharing, it just maps virtual pages in separate address space to the same physical page. Here, the physical page 6. Now we can do things like, for example, here we have a physical page 6 that might be some library code, some precompiled library code that the two processes need, like printf and scanf functions. In virtual memory, we can map part of their virtual address space map to that same physical address where physical page 6 is located. And that way they can share the code for that routine. And since these processes have pages of their own, their illusion that they are the only process that is running in this address space and no other process has an address space. In which case, the process 2, for example, cannot access the physical page 2 because it doesn't have the address for that physical page anywhere in its page tables. So that's a very easy way to keep two processes from stepping on each other's address space, just making sure that they have different physical pages allocated to them. Okay. And lastly, how can we use virtual memory to control read, write, execute permissions within a single process? Well, recall the page table entry. That actually does the trick again. If you remember, there we had a valid bit that tells us whether this entry contains a valid address in physical memory or not, right? But it is not the only information that we can have in this descriptive entity. We can also have a bit, for example, that tells us, do we have a write permission to this area? Or we could only read this area in memory, right? This would be very useful, for example, in the case that when we have two of those shared libraries of code where we might want to be able to read that code, but not necessarily be able to write to it, right? We can also have a bit, for example, that provides permission to execute code in that physical memory, so that we can protect from code injection attacks, which are computer bugs that introduce code into the process code section to change the flow of execution. Okay, so these are quite useful stuff to do, right? And there is a special hardware that checks what kind of memory access do we have. Do we have a read? Do we have a write or an execute permissions for this physical address? And if it's not allowed, then the operating system raises a segmentation fault exception, and the program crashes with an error signal. Okay, so that's how we implement protection of various forms. So coming back to the address translation, and see what happens in the case of a page hit and page miss, or what is called a page fault. Let us first see the page hit. So here it goes. The CPU generates a virtual address using the instructions. This virtual address goes into our memory management unit for translation. The MMU generates a page table entry address. Remember the page table entry address that looks at that page table buffer register to give it the starting address of the page table, and then indexes it appropriately for the virtual address involved, and goes and reads that entry from the main memory. And if it's valid, if there's a valid address there, then the MMU does the mapping, generating the physical address, and accesses the memory again to read that location in the physical memory, and comes back to the CPU with the data. We've done two memory accesses, one to get the page table entry and one to get the actual data from the physical memory. And what happens on a page fault? Well, on a page fault, what happens is that we've gone and gotten our page table entry, brought that back to the memory management unit, and found that the page is invalid. So we now have to go and involve the operating system in helping us get that page from disk and loading it into the physical memory. So that's going to cause an exception that goes to this page fault handler, which is a special piece of code in the operating system that knows what to do with these situations. Then the page fault handler might write the victim page, which is the page it has to replace back into disk. And in case we had written anything to that page, there we want to make sure we are saving that away, so it writes that back to the disk and brings that into the location in physical memory to disk, and then gets the new page from the disk and brings that into the location in physical memory in place of the victim page. Now it has to update the page table entries, and then the CPU can re-execute the instruction which generates a new virtual address. And that is actually the same virtual address, but the CPU needs to reissue it, so that now when we go and read the page table entry, we will find a valid bit set on, and then can execute that instruction safely. Okay, so that is it for virtual memories. To summarize the concepts that we learned in this video series on virtual memories, we discussed programmers and system level view of virtual memory. We saw how these processes have their own linear address space that cannot be corrupted by other processes, and that how the memory is efficiently used by the same principle that works for caches, that is the principle of locality. Virtual memory simplifies memory management and sharing. It also simplifies protection through the simple concept of check bits inside the page table entry, the lookup table. Memory caches are purely a hardware implementation that is related directly to speeding up the execution of programs. okay, and is invisible to the application programmer. And the virtual memory, on the other hand, is key to simplifying process management. That is one of the core functionality of the operating system. The system programmer can allocate or share physical memory among different processes by maintaining the page table entries, and the operating system can handle exceptions. Uh, the virtual memory uses a hardware-based address translation or mapping mechanism that is called a memory management unit. So caches are controlled by hardware versus the virtual memory that is controlled by a combination of operating system and hardware. I hope this series of videos on virtual memory were helpful. In the coming videos, we will talk about some leftover topics that were skipped on purpose to simplify the kind of complex computational structures that are maintained by the operating system, such as the ones such as the process control blocks, the file system, the file system structures, and the page table entries. So stay tuned to my YouTube channel because Tech Instance has a lot more for you. Thank you.